Studica. And today I'd like to share some information with you on the importance of project-based learning for an effective STEM education program, and in particular, I'd like to tell you about the fischertechnik XSTEMLab program. Now, this is a standards-based curriculum involving inquiry, design, and problem solving that was especially created by noted educator and STEM expert Tom White. Now, the following presentation is largely based on a workshop which Tom conducted at the ACTE Career Tech Vision Conference in Atlanta, Georgia in November of 2012. To begin with, what is fischertechnik? Well, as you'll see here, fischertechnik is a flexible and innovative construction system. It was created back in the mid-1960s by noted German inventor Arthur Fischer. Now, unlike other popular construction sets designed to simply stack, fischertechnik was created with more of an engineering mindset. The core building block in fischertechnik is unique in that it allows attachment from all 6 sides, thus it allows for limitless design possibilities. Now, many of the parts slide together to lock in place, and the hundreds of different parts available will also help to address very specific design needs. Now, as you'll see as well, fischertechnik is used by middle schools, high schools, colleges, and universities all over the globe to explore different STEM-related concepts. These would include things like robotics, renewable energies, mechanics, pneumatics, and so on. And it's also been used by numerous companies, including, as you'll see, Porsche, Daimler Chrysler, and BMW, for industrial simulation and training purposes. A way to learn. Well, the picture you see here is from a project that Tom White was asked to help out on last year called The Science of Golf, and it was used in an exposition sponsored by Chevron. Now, the purpose of this exposition was to find ways to get students involved with STEM education. Now, as Tom pointed out in his original presentation, the problem too often with STEM education is that even when there is funding in place, teachers and administrators aren't always exactly sure on the best way to actually go about teaching STEM. Tom feels that an ideal method to do so is by creating exercises like the one pictured. In this case, in this example, students perform various tests on a golf ball in a wind tunnel. And what will happen is certain results will occur, and the students have to discover why they occurred. And the way they find the answers to these questions was through the use of hands-on, project-based learning. Now, according to an article in U.S. News and World Report back in September of last year discussing the state of STEM and jobs, a summary was provided of the results from 3 days of workshops and discussion at the first National STEM Education Conference in Dallas, Texas, that brought together some 1,600 people from hundreds of different organizations and walks of life. And one of the major conclusions that they all agreed on was that hands-on learning that links math and science to the real world works best for all students. Now, as you'll see here, we have a picture of Benjamin Franklin. Tom White was inspired in his creation of the curriculum for the fischertechnik XSTEMLabs by 2 famous people. Of course, Mr. Franklin here, who is quoted addressing the need for better STEM education in his own day, and also Sir Philip Magnus. And here's this quote from Sir Philip where he notes, way back in 1889, the significant difference in learning seen between students who are taught in the normal, lecture-style classroom environment and those who get to experience hands-on learning. Now, what Tom took from these esteemed gentlemen was the need to tie science and mathematics together, as well as the need to provide an avenue for students to engage in the educational process, which results in real learning, as opposed to just the way we've always done it, the approach of lectures and standardized testing. Now, the purpose of STEM education. STEM education needs to provide 3 primary things, capital, if you will, for our society. Not just according to us, but according to the bipartisan Congressional STEM Education Caucus, which is now currently chaired by Dan Lipinski and Roscoe Bartlett. Now, those 3 things are scientists and engineers to perform the research and development to ensure that we maintain our place as a country in the world order. Now, you've probably heard it before, and it isn't an exaggeration. This isn't just an educational concern, it's really a national security issue. It really comes down to, do we want to be dependent on getting our technology from other countries, or will we create and control it ourselves? Will we lead, or will we follow? We also need technologically proficient workers who are comfortable with and versed in the skills required for the modern workforce. And this isn't just a concern for the employers who need such workers. It's also of vital importance to those who would take their place in the workforce because, let's be honest, today's high-paying, high-wage jobs are technology-centered. Third, it provides us with technically literate citizens who can approach the important decisions of today and tomorrow with an understanding of the world we live in. Falling into the gap. Once again, referring to the article from U.S. News and World Report entitled The State of STEM and Jobs. The STEM problem in the United States is most clear when viewed against the gap we see between our high school students and those in China, South Korea, and much of Europe, or the huge volume of mid-level engineers being produced in a place like India. Now, there's a lot of changes that have happened over the last few years. As you'll see here, infrastructure needs have changed. For example, China will build the equivalent of the U.S. infrastructure over the next 20 years. In India, they're going to build the equivalent of the U.S. infrastructure over the next 22 years. Or if you look at a place like Dubai, not that long ago, back in 1970 in fact, the tallest building in Dubai was only 3 stories. As you can see, things have changed a little bit since then. Now, in the meanwhile, industry has also changed. Industry has changed dramatically over the last 100 years. We've gone from the assembly lines and repetitive behaviors of the past, where workers would toil in close quarters, each doing simple piecemeal tasks over and over and over again, to the present day where ever-changing technology demands that new and innovative solutions to problems must constantly be formulated. Now here's another quote from the previously mentioned U.S. News and World Report article. The sweep of industries affected by the STEM skills shortage was revealing, from healthcare, energy, production, and distribution to autos and the whole slowly renewing domestic manufacturing area, including transportation and agriculture. There are no more jobs that require a strong back, said Tom Luce, the force behind the successful National Math and Science Initiative. We have to explain to parents and kids that 30 years ago you could have a living wage job and not be STEM capable. Today, that is not possible. And again, quoting from the previously mentioned U.S. News and World Report article, STEM is not really about the rocket scientists, although a few more would never hurt. It's really about the middle class. It's less about the folks who would design the airplanes than the ones who would build them. Keep in mind, the guy who used to pour the steel now have to know how to program and instruct a robot to do it. Meanwhile, of course, technology has changed. 50 years ago, computers filled a room, and today almost everyone has a smartphone or another handheld device that exceeds the capabilities, the speed, the memory, and storage of anything we might have previously imagined. What's happening while all this is occurring is we have a skills gap. And what you'll see here in this slide, these are some of the skills that our students and our future workforce will need, not only to compete on a personal level, but once again, for us as a country to compete on the world stage. We're going to need students who are going to be versed in measurement, analysis and signal processing, presentation, decision-making, data logging, control systems, because of course we'll need sustainable designs. We're going to need cost-effective use of materials and infrastructure. We're going to need process control. Now, while all that's occurring, what's happening with our students? Well, here's a map, and this shows the potential graduation rates for all 50 states. You'll see the area there where you've got the tan area, that's a less than 70% graduation rate. Where you see the kind of lighter blue-purple area, that's a 70 to 79% graduation rate that's projected. And where you see the darker blue, that's an 80% or higher graduation rate that's expected. But as Tom White pointed out in his original presentation, due to the way in which the map was devised, for example, they included students who were choosing to drop out of school, but who claimed that they would pursue a GED as being potential graduates. In actuality, the rates here are quite generous. In truth, it's probably fair to say that a good 30% of the student population is underperforming. Meanwhile, right at this moment, 3 million job openings in the United States remain unfilled, and at the same time, our unemployment rate is hovering near 8%, primarily because the workers who are available to try to fill those positions do not have the background, knowledge, or of course the qualifications to do so. Which brings up the question, how has education changed? Well, 100 years ago, students were arranged in nice orderly rows, listened to lectures given by a teacher who might share examples on a blackboard, and then took tests to see how much they had retained. And today, in many modern public schools, students still follow the passive model of sitting in rows, listening to lectures, and taking standardized tests. Yes, you might have a few more computers around here and there, but really not much has changed. Now here's some food for thought. At the top here, right next to the number 3, you'll see this is an example of how one student answered a common geometry question. Find x. Well, they circled it and they found it. Here it is. Now this would be funny if it wasn't unfortunately too tragically common. The problem is that too often students encounter things in schools that just seem too abstract to ever be useful in their lives. And what happened here is that no one has helped them to make the connections. And so what will happen is they keep asking the same 3 questions. Why do I need to know this? Where will I ever use this? And what do I need to do to get an A? And with this kind of approach, can you blame them? Now, essentially, the current educational system is based upon the model created in 1907 with the help of the Carnegie Foundation. Now, back then, students were deemed as fit for college based on certain requirements they had met, for example, how many years of math or reading, etc., but all based on the needs of that society in that time. Keep in mind, back then, students would go to work in factories where they needed not to ask questions or solve problems, they just needed to know how to follow directions. But now, 100 years later, our needs are quite the opposite. Now, in fact, we need students who can ask questions, and we need students who can solve problems. And that brings us to the fischertechnik XSTEMLab program, which incorporates state-of-the-art fischertechnik construction system, the state-of-the-art fischertechnik construction system, with specially created curriculum, with the idea of creating a project-based learning experience with the focus on addressing current educational standards. Now, Tom White built this curriculum around fischertechnik because he truly believes that fischertechnik is the ideal construction set for an engineering-based curriculum program such as this. Now, the materials can all be used and reused. Things that are built can be taken apart and reassembled into something completely different. And it's much more economical than purchasing an expensive piece of equipment that might be used for 1 or 2 experiments or projects and then put on a shelf until the next semester's class. And it should go without saying, it offers limitless creative possibilities. Now, the major goals of the fischertechnik XSTEMLab program. Well, when Tom put together the fischertechnik XSTEMLab program, he had several goals in mind. First, based upon his observation that various types of teachers have different strong points. For example, he sees his own strong suit as being the creation of curriculum more so than conducting a lecture. With this in mind, he focused on creating a curriculum that would provide a broad foundation of tools for all types of teachers to be successful in providing this class, so that they could instead focus on the needs of the students. Essentially, what you have here is a turnkey solution that would provide everything they would need in one place. Now, the curriculum was designed to provide a clear roadmap for both teachers and students, with the learning facilitated through the extensive use of projects and problems for the students to address. The goal was also to enable teachers to provide students with engaging curriculum-based projects that had an authentic objective in solving real-world problems and which contained embedded academics. Now, I'd also like to point out that the Common Core standards addressed in this curriculum are the current standards in place. Keep in mind, reading no longer means just reading and understanding literature. It also refers to being able to read technical documents. And likewise, meeting the current writing standards now also means that a student should be able to write technical documents, and so on. What students experience? Now, under this project-focused model, students are told upfront what they need to learn and understand, and they're provided with different tools and pathways to achieve this goal. Among other things, students must learn the documentation process. For example, they create a design brief, they keep a digital engineering journal, things of this nature. They're going to do research outside of class and homework as well, and they're going to collect data. They're going to learn firsthand how data acquisition works, how to process data, how to put the data into graphs and other formats, and so on. They're going to be given technical literacy tasks driven by the project. They're going to acquire knowledge through the inquiry and exploratory research designed to give them the tools to solve a problem. They're going to acquire the necessary science, mathematics, and technical skills through carefully designed enabling activities. Students will create prototypes of their solutions, utilizing, as you'll see here, the advanced fischertechnik modeling system. They're going to then create programming solutions to control those prototypes. And at the end, they're going to create the final documentation for the entire project and present the findings. Now here we have a slide, and this outlines the themes for the high school mechatronics project. This is what you'll find included with the curriculum disc for the high school STEMLab. And if we just go down the list here, you'll see that among the areas addressed, sketching and documentation, which of course is documenting the whole process, the trial, the error, everything that's involved. They're going to learn about structures. They'll learn about, for example, the basics of different types of structures and testing various designs. One example that's used in the STEMLab curriculum is learning about the structures of different roller coasters and then studying the physics involved, etc. Mechanical systems, for example, how do gears work? Electronic systems, learning how circuits work, how things are wired, and so on. Control systems, how they're used. Sensors, what do they do? How are they used? Etc. and on into the fundamentals of robotics and automation. Now for the next slide, we have an overview of the middle school project themes. And as you'll see, it's similar in many ways to the high school version, but essentially it offers a more basic version of many of the themes that appear in that set. With the emphasis here more on providing the basic groundwork needed to be an informed and literate citizen in our modern technology-based society. Now, here we have an outline of the curriculum structure, and this would apply to both the middle school and the high school versions of the STEMLab program. For each unit addressed in those programs, it's going to be just as you see here. The purpose will be addressed, the concepts, the student deliverables, the assessment and evaluation, an outline, standards, an authentic project scenario, a daily teaching plan, supporting activities, and resources. Now, at this point, I think it would be helpful to show you what the actual curriculum for the fischertechnik STEMLab program looks like. Now, keep in mind that with each set, either the middle school version or the high school version, each of them contains a disk with the complete curriculum. Now, right now, let's insert the disk for the high school STEMLab into our computer. And there we go. And here's what you will see on your screen when you open the high school version of the STEMLab curriculum disk. Now, as you'll see, it contains both a teacher version, right here, and a student version, as well as the ROBO Pro software, which is used to program the various fischertechnik robotic models. Now, the student version of the program, this is something that can be distributed to the students, of course, is essentially the same as the teacher version, but it's minus the standards-related material, the rubrics, and the other instructor exclusive material that would be included. Now, let's take a look at a sample unit to see how the curriculum is organized. So let me just get out of this for a second. And we'll wait for our screen to refresh. And this is what happens when you click on the teacher version. As you'll see, we have the screen here. We have the list of all the themes, all the unit themes, all the little sub-chapters there, and all the folders. And let's just kind of go to an example here to show you again how the curriculum is laid out. We're going to look at the Introduction to Programming segment here. Okay, and what you should see right here is we've got a little layout. This picture here is a graphic representation of the ROBO Pro software. Now, as you will see, it's designed to use icons to represent the different actions, which students will arrange in a flowchart manner to create the program for their robots. Now, ROBO Pro is great because it allows students who may not have any prior experience with programming of this sort to quickly become comfortable with doing so. Anyway, so we're going to be addressing programming in this section. So the first thing we have under programming is, of course, the purpose of the project. Now this is the section that spells out the purpose of the project, of course, why are we doing this, as well as what we hope to accomplish here. So it's all laid out here. For example, it's going to be designed to help students to identify and apply appropriate methodology associated with logic, utilize mathematical analysis, scientific inquiry, and engineering design to develop solutions to open-ended problems, access, generate, process, and transfer information using appropriate technologies, and so on. So that's your whole purpose is spelled out there. Then we get into the concepts. Now this outlines, of course, the concepts to be addressed, the big things that you're going to learn from this project, and what's really important and useful and vital to understand and know, not only for what you're doing right now in the project, but these are the things that the students are going to need to take with them as they move on in their careers. We then get into an outline. Let me just scroll down here. As you'll see, the outline, it spells out exactly what's covered in the project. For example, the methods of writing programs with the flowcharts, word problems, and so on, the program characteristics, documenting programs, object blocks, variables and constraints, loops, branching, data, and so on. Now we get into the standards. And this is where the specific standards to be met by this particular project section are spelled out. Keep in mind that for each of these units, each of these theme units, they're going to have different standards that are being addressed, and it's going to be spelled out in each of these sections. Anyways, you see as we scroll down here, we have Common Core math standards that are being met, interpreting functions, building functions, linear, quadratic, and exponential models, modeling with geometry, etc. Then you get into the reading standards for literacy in history and social studies, key ideas and details, integration of knowledge and ideas. You get into the writing standards for literacy in history, social science, or social studies, science, and technology. Once again, you'll see that this is really, the whole idea of STEM here is tying all these different areas together. It's not merely science in a box. It's not merely technology in a box. It's bringing the math elements in. It's bringing the writing and the reading and all of these things together. But then, of course, we do get into the science. So we have the NSES content standard for K-12. You have standards for technological literacy all spelled out here for this section. The ISTE-based standards. All spelled out there. Now we get into the assessment. Now right here it's spelled out, of course, how the student performance will be assessed. For example, looking at the general rubrics for literacy, we'll pick on the argumentative persuasive rubrics here. And what we have here is we have a rubric for assessing the student's presentations. For example, the focus of their argument here. Is it lacking in focus? Not yet. Answering the problem and stating a position, but still weak, which would be getting there. Are they answering the problem with a clear and generally convincing and generally focused argument, which means they meet the expectations? Or do they fully answer the problem with a very clear focus and a strong and convincing argument, which would be exceeding expectations? Now keep in mind, of course, that these rubrics are included for each of these units and provide the parameters for assessing the student performance in each section. Now, this is the process for seeing if the student is actually meeting the Common Core standards, of course. There's also an area on persuasive and informational writing, what have you. Okay, now we get to the essential question. Now, this is the big idea. Why is this important? Now, how well students answer this question is how we see if they understand all the pieces. And here we see the question is, how can we make decisions electronically, removing the need for human intervention? So once again, this is talking about students doing something where they're going to get into programming so that they don't have to be there to actually control the machine while all this is taking place. And then we have the student scenario. And here is the real world scenario the student is given. This is essentially an answer to where will I ever use this. Now in this particular example, they are given the scenario of being a controller programmer at a programming company that specializes in designing elevators and writing the control packages for their clients. Now in this scenario, they will be required to program the elevator to perform certain functions. For example, how will it respond to a call button being pushed on different floors at the same time? Which floor is it going to go to first? Now in this whole scenario, the clients, the hypothetical clients, are spelling out their requirements, and the students will be required to create a program to address these specific needs. Then they're going to create a prototype and prepare a presentation for their fictional clients that's going to have to include a demonstration of the prototype and the program in action. Then we get into the daily plan. Day 1, day 2, day 3, day 4, and so on. And these are the expectations for the project, as you'll see here. Now, each day of the plan acts as a guideline. It spells out specifically what we are looking at today and what we want to accomplish long range. And each day's activities provide a building block towards the big project that the students will be required to complete at the very end. Now, we'll see there are links here for the different things that are discussed. For example, if it's an engineering notebook and we want to know, the students want to know, the teacher want to know what's involved in that, we can click on that link. And of course, it will spell out exactly what's required for an engineering notebook. The same would be for a design brief, an engineering report, how that's laid out, title page, summary, nomenclature, etc. All of it's put right in there. Also, if you have issues with, for example, installing the software, it's going to walk you through installing the ROBO Pro or installing drivers if you need those, what have you. Once again, each day has different activities, has different links that are going to pertain to what's being addressed there. Different questions. For example, on day 7 here, we have the question about how does my dishwasher know when the dishes are clean? Of course, as anyone would know, your dishwasher doesn't actually know when they're clean, but it's programmed a certain way to go through certain cycles for a specific period of time. So students are going to learn about that, and of course, it's all going to be related to this elevator exercise that they're doing in this section. Of course, other things that are covered in this section will include how data is taken from a sensor and recorded, taking files from the ROBO Pro software to Excel to be worked on, then putting them back again, working on robotic positioning, things of this nature. And again, each unit builds on the one before it, and each unit is subsequently gets more complex. Now, at the very end, as I mentioned before, there's a big open-ended project. And this is where students must combine all the things they've learned and worked with in the units before. And this is really what helps to reinforce for students what it's all about. So, of course, we just scroll through all these daily activities. How do programs make decisions on the information they gather and they're given a task, what have you. And this goes on quite extensively, day 18, 19, 20, and we go up to day 35. Then after that, we have some resources. We have vocabulary spelled out. You see here are a list of terms that are encountered during the project. We have resources. These are the various resources included, web-based resources that we have to note very carefully selected. Now, during the course of the lab, students are going to be required to do background research and reading as well. And as much of this research is going to be internet-based, as of course it is these days, students are going to learn how to find the good information and how to make the differentiation between that good information and all of the questionable and sometimes shoddy information that can be found on the internet. You also get down to a section of you have the Word documents with all of this different area. These are things you can print out if you want to look at digital branching. You can get a Word document for that. Installing ROBO Pro, the flow charts, logic gates, variables, rubrics are available as documents as well. You have PDFs, you have PowerPoints, all of these things. Now, going back again, keep in mind, this is for all these sections. There's a lot of material here, giving you background on project-based STEM education in the introduction, talking about the assessment and rubric documents, giving you access to the fischertechnik manuals, which I will talk about in a second here. Sample ROBO Pro programs, we'll mention that. Installing ROBO Pro. We get into the sketching and documentation. Here, once again, this is going with each theme, as I had mentioned before. You've got a project guide for that. You've got sketching activities. You go into the engineering notebook, the design brief, the engineering report. So each of these sections, each of these themes has these little subsections where they're going to go through point by point the mechanical systems as we discussed. They get a project guide for that. They get linkage diagrams. When they get into structures, they're going to do different things here, learning about mechanical energy, having an answer sheet here, roller coaster simulation, etc. And just going on down the line for all of these things. So let's go back to our PowerPoint here. Yeah, we're just lagging a second. Okay, now also included on the curriculum disc, as you saw in the one section there, are PDF versions of the current fischertechnik construction manuals. Now the reason for that is during the course of the curriculum, students will be asked to build models from these manuals, or sections of models in some cases, just basically to familiarize themselves with how the fischertechnik construction system works, and also how different subassemblies are built. And here are some examples that are used in the STEMLab curriculum. Here we have a simulation of a pinball machine, which will involve different sensors and programming and what have you. Here you have a robot that might be seen in an industrial simulation. It's a mechanical arm that's doing stacking functions. Here's another robotic arm that pivots. Here is what's called the TX Explorer. It's a line follower. You have different sensors on there, ultrasonic sensors and what have you. And here's a little simple elevator model. Now again, keep in mind, the material here in the fischertechnik manuals is included just to help students to address some of the more basic daily activities and to learn, again, how these different subsystems work and how the fischertechnik system itself works, because once again, it's a unique system. Now they're going to use this knowledge to address the many other small projects where everything isn't spelled out for them, such as, for example, creating the elevator prototype in the sample unit we discussed, which I also must note will need to be much more elaborate than the simple model that you see here. And of course, then they're going to use this knowledge as well at the large cumulative project at the very end. And as we also saw there, the ROBO Pro software that's included also contains sample files for the various models so that you'll have examples to work from. And as you saw, that's right at the beginning of the curriculum again. Once again, there's detailed information included on installing the ROBO Pro software and how to configure the ROBO TX Controller and so on. So once again, you have all that background material here so that you're not working in the dark. You have everything to, if you have any questions as you move along, you have those areas that you can just access easily. Now, each of the STEMLab kits, whether it's the high school version or the middle school version, comes packed in its own plastic sorting box for organized storage, as you'll see here. And each set includes all of the parts needed. Everything you need is in that one box. The software, the TX controller, the parts, what have you, the curriculum disc, it's all in there in each set. So, how many kits would you use in a classroom? Well, per Tom White, he recommends ideally one kit per 2 students for the middle school STEMLab level. And the reason for that is this will keep each student fully engaged and involved in the activity as opposed to, let's say, just having 2 students working and other students just observing them, which is never a situation you want. So if you're looking at the middle school STEMLab set, you really want to think about 2 students per set. Now, when you get to the high school section, the one that we were scrolling through in this presentation, due to the more involved nature of the projects, you could actually get away with 3 or even 4 students per set. Ideally, though, the smaller the group of students per set, the better. So, with this in mind, the average classroom of, let's say, 20 students would use anywhere from 5 to 10 STEMLab sets, depending, again, of course, on the section that you're covering. Are you doing the middle school version? Or are you doing the high school version? And whatever budget you're working with. But again, aim for 2 students per set. Now on that note, we'd like to thank you very much for taking the time to view this presentation. If you have any questions, if you'd like more information on the fischertechnik STEMLab program, pricing, quotes, what have you, or if you'd like to speak with one of our dedicated educational representatives, the one for your state, please call us at Studica. As you'll see, our number right here is 888-561-7521. You can, of course, also visit our webpage, which you'll see right there, and that's www.studica.com/fischertechnik, FISCHERTECHNIK, -STEM-lab-program, or easier still, you can just email us at STEMLab@studica.com. On that note, I'd like to thank you very much for your time, and we look forward to speaking with you soon.